There is a machine out there, right now, moving, alone. It has no crew, no fuel to replenish, no way to call for help if something goes wrong. It was built before the internet existed, before cell phones, before personal computers. It carries 8-track technology into the fabric of interstellar space. And yet, against every law of probability, against every expectation of every engineer who ever worked on it, Voyager 2 is still transmitting, still sending back data from a place no humans being has ever been. But here is what nobody is talking about. The data it is sending back is rewriting everything. Nobody told you the full story, and that is exactly the problem. When most people hear the name of Voyager 2, they picture something nostalgic, a relic from a different era, a golden record, some grainy photographs of Jupiter, a pat on the back for 1970s American engineering, something to celebrate and then move on from. What they do not picture is a spacecraft that, in the year 2026, is actively dismantling the models scientists spent decades building. They do not picture a machine operating at the very edge of what physics says should be possible, transmitting signals that take over 19 hours to reach Earth one way, signals that arrive so faint they require some of the most sensitive antenna arrays ever constructed just to detect them. They do not picture a 47-year-old probe that is, at this very moment, floating approximately 143 astronomical units from the Sun, that is over 13 billion miles, still working, still observing, still teaching us things we were not prepared to learn. The discoveries Voyager 2 has made in the last several years are not the kind that fit neatly into a press release. They are not the kind that generate satisfying headlines or clean explanations. What Voyager 2 has been sending back from the frontier of our solar system and the interstellar space beyond it is something far more unsettling. Evidence that our most fundamental assumptions about the universe we live in were wrong. Not slightly off, not in need of minor adjustment. Wrong in ways that force scientists to go back to the beginning and start over. We launched this spacecraft in 1977. Its original mission was designed to last 5 years. 5 years to swing by Jupiter and Saturn and collect whatever data it could before the mission was declared complete and everyone went home. That was the plan. 20th, 1977 genuinely believed they were launching something that would still be sending back revolutionary science nearly half a century later. Nobody planned for this. And yet here we are in 2026 with Voyager 2, doing things that its creators could never have anticipated, from a location no human-built object had ever reached before it got there. To understand what Voyager 2 has discovered, you have to understand what it crossed. In November 2018, the spacecraft crossed the heliopause. That word sounds technical, and it is, but the concept is profound. The heliopause is the boundary where the sun's influence ends. Every star you have ever looked at in the night sky produces something called stellar wind, a constant stream of charged particles that radiates outward in all directions. Our sun does this too. That stream of solar wind pushes outward against the cold interstellar medium, the ancient gas and dust and plasma that fills the galaxy, and the point where those two forces perfectly balance each other, where the outward pressure of our solar wind can no longer push any further against the pressure of everything else, that point is the heliopause. That is the edge of our solar system. That is the door. And what it found on the other side shocked the people who had spent their entire careers preparing for this moment. According to data published in a series of peer-reviewed papers, when Voyager 2 crossed the heliopause, its instruments recorded something the models had not predicted with accuracy. The plasma on the other side, the very local interstellar medium, as scientists call it, was hotter than expected. Not slightly warmer. Hotter in a way that defied the theoretical framework scientists had constructed over decades. The interstellar medium was supposed to be a region of cold, dense plasma. Colder than inside our heliosphere. More dense, yes, and that part checked out with us. Measurements confirming a plasma density jump of approximately a factor of 20 the moment Voyager 2 crossed the boundary. But the temperature readings told a different story. The interstellar medium near the heliopause was running hotter than any model had predicted, and nobody has fully explained why. This is not a minor discrepancy. This is not a rounding error. When one of the most fundamental physical regions of our solar system behaves differently than our best theories say it should, it means the theories need to be rebuilt. It means that everything we thought we understood about how our heliosphere interacts with the rest of the galaxy is built on assumptions that do not hold at the boundary where reality actually unfolds. And the only reason we know this, the only reason anyone on Earth has any data from that region at all, is because of one old spacecraft that was supposed to stop transmitting decades ago. But the interstellar plasma anomaly is not even the biggest discovery, not by a long shot. Because while scientists have been processing Voyager 2's interstellar data, something else has been quietly emerging from decades of archived observations. Something that nobody noticed at the time. Something that Voyager 2 recorded 40 years ago, and that researchers have only recently had the tools, the computing power, and the theoretical frameworks to understand. And what they found when they went back to those old readings has fundamentally changed the way we think about an entire planet in our own solar system. The year was 1986. Voyager 2 made its historic flyby of Uranus, the only close-range encounter with that planet in human history. The spacecraft swept past at over 35,000 miles per hour, its instruments drinking in as much data as they could in the brief window of proximity. And among those readings was something that stopped scientists cold. Uranus had a radiation belt. Not unusual. Most planets with magnetic fields have them. But Uranus's electron radiation belt was not behaving the way it should. It was off the charts. The readings showed an electron radiation belt far stronger than anything the existing models said was possible for a planet like Uranus. Based on every comparison with other planetary systems, based on every formula scientists had for predicting radiation belt strength, Uranus should not have been able to sustain anything close to what Voyager 2 was recording. So they filed it away. They noted the anomaly, they debated it, wrote papers about it, and ultimately arrived at an unsatisfying consensus. Uranus is just weird. The planet is already one of the most bizarre objects in the solar system. It rotates on its side, with its poles pointing roughly toward the sun rather than perpendicular to its orbit, and its magnetic field is wildly offset and tilted in ways that have no clear analog anywhere else in the solar neighborhood. So scientists chalked up the strange radiation belt readings to Uranus being Uranus, and they moved on. In research published in Geophysical Research Letters and analyzed by teams at the Southwest Research Institute, scientists have gone back to those 1986 Voyager 2 readings with something they did not have in 1986. 4 decades of additional data about how space weather actually works, gathered from instruments at Earth from satellite. Observations from events like the powerful solar storm of 2019 that dramatically accelerated electrons in Earth's own radiation belts in ways that closely mirror what Voyager 2 recorded at Uranus. And when researchers compared those modern Earth-based observations against the old Uranus readings, the picture that emerged was extraordinary. According to the new analysis, scientists now believe that when Voyager 2 flew past Uranus in January 1986, the planet was being hit by something called a co-rotating interaction region. A co-rotating interaction region, or CIR, is a powerful space weather event caused when fast-moving streams of solar wind overtake slower-moving streams. The resulting collision zone creates a compressed high-energy region that propagates outward through the solar system. When one of these events slams into a planet with a magnetic field, the results can be dramatic. On Earth in 2019, scientists watched a CIR event cause an immense spike in radiation belt electron acceleration, the kind of event that can damage satellites, disrupt GPS signals, and push aurora displays to latitudes where they are never normally seen. That 2019 Earth event, in the words of researchers involved in the new study, bears a striking resemblance to what Voyager 2 recorded at Uranus 33 years earlier. For nearly 4 decades, the scientific community operated on the assumption that Uranus possessed an inherently extreme radiation environment. Papers were written, models were built. The entire understanding of Uranus as a planetary system was structured around readings that were, according to this new research, not representative of normal conditions at all. Voyager 2 had, by extraordinary cosmic coincidence, flown through Uranus's system during a rare, transient space weather event, a moment in time that made everything look more energetic, more intense, more extreme than it typically is. The spacecraft captured a snapshot of Uranus during what might be described as a planetary emergency. And for almost 40 years, scientists treated that snapshot as a portrait. The practical implications are enormous. Understanding that Uranus's radiation environment may be far less extreme under normal conditions than the Voyager data suggested changes the calculus for future missions to that planet. It changes what kinds of instruments a future spacecraft would need to carry, what kinds of shielding would be required, what scientists would expect to find when they arrive. It reopens questions about Uranus's internal structure, about the behavior of its uniquely tilted magnetic field, about whether the icy giant might be more geologically active and more dynamic than anyone has assumed. The new research does not answer those questions. What it does is prove that the one dataset we thought we had, the Voyager 2 flyby readings, was telling us a story about a specific moment rather than a general truth. Because Uranus, in the current landscape of planetary science, is already a priority target. NASA's Planetary Science Decadal Survey has identified a Uranus orbiter as the top recommended flagship mission of the current decade. Scientists want to go back. They need to go back. Uranus and Neptune, the ice giants, are the least explored class of planet in our solar system and the only direct. Data we have from either of them came from Voyager 2's brief flybys in 1986 and 1989, respectively. Everything we know about those planets is based on a few hours of close observation, and now we know that at least some of those hours were spent during anomalous conditions. Meanwhile, as these revelations emerge from the archives, the spacecraft responsible for generating them is facing a crisis of its own. Voyager 2, already performing a feat of engineering endurance that has no parallel in the history of spaceflight, is running out of power. Not gradually, not in some theoretical future sense. Running out of power right now in ways that are forcing NASA to make decisions with permanent consequences. Each of Voyager 2's science instruments requires electrical power. That power comes from radioisotope thermoelectric generators, RTGs, which convert the heat from radioactive decay into electricity. When Voyager 2 launched in 1977, those RTGs were producing roughly 470 watts. As of today, that figure has fallen to somewhere around 40 watts, less than a standard light bulb, and it continues to decline at approximately 4 watts per year. That is the margin NASA is working with, 4 watts per year. In September 2024, mission engineers made the decision to shut down Voyager 2's plasma science instrument. This was not a technical failure. The instrument still worked, but it was drawing power that the spacecraft could no longer afford to give it, and its orientation relative to the interstellar plasma flow meant its data return had been increasingly limited for years. It was the most practical sacrifice, but it was still a sacrifice. Humanity permanently gave up one of its only active instruments in interstellar space, one of its only windows into a region of the universe where no other probe has ever operated. Then, in March 2025, Voyager 2's low-energy charged particle instrument was powered down. Gone. Another eye closed forever at a distance of more than 12.5 billion miles from Earth. According to NASA, Voyager 2 will continue operating its magnetic field instrument and its plasma wave subsystem for the foreseeable future. Its cosmic ray subsystem is scheduled to be shut off in 2026, this year. After that, the configuration becomes increasingly minimal. The engineering team at JPL believes the spacecraft can sustain at least one active science instrument into the 2030s, but they are careful to add a caveat that 47 years in deep space can produce unforeseen challenges at any moment. Every signal that arrives from Voyager 2, a signal that takes over 19 hours to travel from the spacecraft to Earth at the speed of light, is now treated as a gift rather than a guarantee. There is something almost unbearable about that reality. Consider the geometry of what NASA's engineers are doing when they send a command to Voyager 2. They transmit a signal. It travels at 186,000 miles per second, and it still takes 19 hours to arrive. Then they wait another 19 hours for a confirmation to come back. 38 hours minimum to find out whether a command worked. 38 hours during which the spacecraft is operating alone without guidance, in a region of space that no model fully describes, carrying instruments whose every reading is irreplaceable. The people managing this mission are not working with the luxury of real-time feedback. They are writing letters to a traveler at the edge of the known world and waiting more than a day and a half to find out if the letter arrived. According to informed sources within the space science community, the pressure surrounding these decisions is unlike anything else in active mission management. Every instrument shutdown is deliberated over for months. The question is never purely technical. Which instrument uses the least power, which provides the least marginal data? Because the secondary question is always harder. What might we miss? What question? Might that instrument have answered? What phenomenon might it have detected? What discovery might it have enabled that we are now closing the door on permanently? Nobody can answer that question. That is precisely what makes the decision so difficult. In the words of Suzanne Dodd, Voyager's project manager at JPL, if we don't turn off an instrument on each Voyager now, they would probably have only a few more months of power before we would need to declare end of mission. The choice is not between keeping everything and losing something. The choice is between controlled sacrifice and total silence. What most people are not seeing is that even in this twilight state, even with instruments going dark one by one, Voyager 2 continues to contribute science that cannot be replicated by any other means. The plasma wave subsystem, which remains active, is measuring the density of interstellar electrons in real time, and those measurements are revealing that the density of the interstellar medium is not constant. It is increasing. As Voyager 2 moves deeper into the very local interstellar medium, the electron density readings have been climbing, suggesting that the spacecraft is approaching a region of compression, possibly where the interstellar medium piles up against the outer boundary of our heliosphere like snow accumulating in front of a plow. According to researchers, Voyager 2 is now approximately 143 astronomical units from the Sun, and still approaching what models suggest will be a peak in plasma and neutral atom density somewhere between 200 and 250 astronomical units. That destination is decades away, if the spacecraft survives that long, but it might not need to arrive there to complete its most important work. because Voyager 2's most powerful contribution in its final operational years may not be the new data it collects, but the old data it already has. Data that scientists are still mining, still reanalyzing, still finding surprises in as the theoretical tools available to them continue to evolve. The Uranus radiation belt story is only the most recent example. The same pattern has played out multiple times in Voyager 2's history. Observations made during the planetary flyby phase of the mission in the late 1970s and 1980s have been revisited and reinterpreted as better analytical tools became available, and each reinterpretation has revealed something that the original analysts missed. Active volcanoes were confirmed on Jupiter's moon, Io. The fine why? Structure of Saturn's rings, first photographed by Voyager, is still being studied for its implications about the dynamics of ring systems around other planets. The magnetic field configuration at the heliopause, where Voyager 2 detected a field that ran parallel to the field inside the heliosphere, in a pattern that stunned the scientists who expected the two to be misaligned, remains an open question that nobody has cleanly answered. The spacecraft spent decades reaching that boundary, and the data it sent back when it got there is still being processed. We tend to think of space missions as linear. The spacecraft launches, flies, arrives, transmits, finishes. We think of discovery as a moment. The image arrives on a screen, a scientist gasps, a press conference happens, and we move on. An ongoing, iterative, perpetually unfolding investigation that does not follow the rules of a news cycle or a funding cycle or a human attention span. The discoveries from this mission accumulate across decades. They happen when a graduate student decides to look at archived readings through the lens of a theory that did not exist when the readings were taken. They happen when a solar event near Earth provides a new framework for understanding a reading from a planet 2 billion miles away. They happen when two datasets separated by 40 years suddenly illuminate each other. What the mainstream coverage misses, what the headline writers consistently fail to grasp, is that Voyager 2 is not a story about the past. It is not a monument to the 1970s or a chapter in the history of the Cold War space race. It is an active, present-tense scientific instrument that is simultaneously sending back new data from interstellar space and providing the historical archive against which all of our new understanding of the outer solar system is measured. It is the only yardstick we have for regions of the universe where no other human-made object has ever traveled. The magnetic field instrument will keep running for now. The plasma wave subsystem will keep listening. The cosmic ray subsystem will be switched off this year. Engineers believe, carefully, cautiously, that at least one instrument can keep operating into the 2030s, but the mathematics of radioactive decay does not negotiate. In 47 years of continuous operation in the radiation environment of deep space has taken a toll that no amount of engineering ingenuity can fully overcome. The team at JPL is managing a slow-motion finale that is being played out across years and light hours, one instrument shut down at a time, one 19-hour delayed command at a time, at the very edge of what is technically possible and far beyond what was ever planned. In the words of the team themselves, every day could be their last. Consider for a moment what will happen when Voyager 2 finally falls silent. When the last signal arrives, when the last instrument draws its last data point and the power finally drops below the threshold needed to maintain communication, there will be no second chance. No rescue mission, no software update beamed across 13 billion miles to bring it back online. The silence will be permanent. And in that silence, a chapter of human exploration will close. A chapter that opened not when Voyager 2 was launched, but when it crossed the heliopause, when it became the second object humanity has ever sent into the space between the stars, when it began sending back the first direct measurements of a region that has existed since before the Earth formed, a region that will continue to exist long after everything we have ever built has turned to dust. The real story of Voyager 2 is not what it found. It is what those findings keep revealing, even now, even as the spacecraft slowly powers down, even as the signals grow fainter, even as the instruments go dark one by one. Because the data does not disappear with the spacecraft. The terabytes of archived readings from 47 years of exploration remain, available to any scientist with a new question and the analytical tools to pursue it, available to graduate students not yet born who will one day write the papers that finally explain the anomalies still sitting in those datasets unexplained. The hotness of the interstellar medium near the heliopause, the mystery of the parallel magnetic fields on either side of the boundary, the Uranus radiation readings that turned out to be a portrait of a storm rather than a portrait of a planet. These are not closed questions. They are open files, active investigations, puzzles that sit in archived databases, waiting for the right mind to crack them. And here's the question nobody in the mainstream conversation is asking. If 40 years of reanalysis have already produced discoveries this significant, what else is hiding in those numbers? What phenomenon did Voyager 2 measure in 1980 or 1989 or 2005 or 2020 that we have not yet had the theory to recognize? What question will a scientist ask in 2035 or 2050, armed with tools that do not yet exist, that will send them back to the Voyager 2 archive and produce an answer that changes everything again? We do not know. That is the point. We cannot know. And that uncertainties, that irreducible, perpetual openness of what Voyager 2 has left behind and continues to send back, is not a weakness. It is the most powerful thing about this mission. It is what separates Voyager 2 from every other scientific undertaking in the history of human spaceflight. Most missions end. Most discoveries are made and filed and taught in textbooks and eventually taken for granted. Voyager 2's legacy is different. Its legacy is not a fact. Its legacy is a question that keeps changing shape, keeps finding new dimensions, keeps producing new answers every time someone smart enough to ask the right question goes looking in the right place. Out there right now, in the dark between the stars, at a distance so vast that the fastest thing in the universe takes 19 hours to cross it, something humanity built in 1977 is still moving, still operating, still watching, and still, against every reasonable expectation, still talking. The question is whether we are still listening closely enough, because the data that probe has already sent back contains discoveries we have not made yet, and the window in which it can send us anything more is closing, instrument by instrument, watt by watt, year by year, faster than most people realize. When Voyager 2 finally goes quiet, the universe will not explain itself again. There will be no replacement. There is no mission currently planned that will reach the heliopause within the next several decades. Whatever Voyager 2 does not tell us in the time it has left is information that this generation of scientists, and possibly the next, will simply not have. What happens to science without its only source? What happens to our understanding of interstellar space when the last instrument measuring it from the inside goes dark? What is out there, past 143 astronomical units, past the region of increasing density, past the zone where models start to break down? What is out there that we have not asked the right question about yet? Somewhere between here and an answer that does not exist yet, a 47-year-old machine is still moving, still transmitting, still, against all odds, doing exactly what it was built to do, but not for much longer.